All right, our fourth speaker in this session is going to be Tunado Naka, swap my vowels. And he is a researcher at Mitsubishi Electric Corporation, and his talk today is going to, if I recall correctly, go a bit into a defense as it relates to / aimed at membership inference attacks.
Thank you for the introduction. Hello everyone, I'm Tsunato Nakai from Mitsubishi Electric. Today I would like to talk about SEDMA, Self-Distillation with module aggregation for membership privacy. This slide shows the overview of this presentation. We propose a new defense method against membership inference attacks, which identify whether a target sample was used in training data. Also, membership inference attacks are important measure to evaluate the potential risk of privacy leakage from trained model. Defenses against membership inference attacks are classified into two categories: probable privacy defenses and empirical membership privacy defenses. Empirical membership privacy defenses aim to preserve the model utility. So in this presentation, we introduce a new empirical membership privacy defense named SEDMA, which outperforms state-of-the-art defenses such as KCD and SEDMA in achieving the lowest risk of privacy leakage. This is an outline. First, as a background, I explained empirical membership privacy defenses. Next, from the challenges of previous work, I will explain our goals for privacy defenses. Next, I will propose a new defense called SEDMA based on self-distillation using model aggregation. In the experiment, we will show the evaluation result of SEDMA on the 3 benchmark data set. Finally, I will summarize this presentation. The defenses against membership inference attacks are classified into 2 categories. Probable privacy defenses provide privacy guarantee, however, degrade model utility. On the other hand, empirical membership privacy defenses maintain high model utility but cannot provide probable privacy guarantees. In this study, we focused on empirical membership privacy defenses. There are some empirical membership privacy defenses such as Aggregation, MemGuard, KCD, and SEDMA. The state-of-the-art defenses have achieved good privacy utility trade-off by using knowledge distribution on split training dataset like KCD and SEDMA. In this study, we propose an empirical membership privacy defense for 3 goals: low attack accuracy, high model accuracy, and low computational cost. For low attack accuracy, we conduct 2 types of attack: single query attack and label on the attack. We conduct 9 attacks in total to evaluate attack accuracy. For high model accuracy, we compared with state-of-the-art defenses, KCD and SEDMA, to evaluate privacy utility trade-off. Also, it is not practical if the additional computational cost for the defenses is significant. For example, according to SEDMA experiment in the paper, the 25 trend model are required for good trade-off. So next, I will explain the KCD and SEDMA and our defense. Our defense aims to achieve these goals. In KCD, the KCD defense consists of 3 steps. First, KCD make combinations of split training data and trained multiple submodels on each combination. Next, the submodels label the prediction results for each one remaining untrained split training data and make a data set with the label data. It is called soft label. In the inference phase, it output a prediction result by using mitigated model trained on the dataset with soft labels. in SEDMA defense also consists of 3 steps. First, SEDMA trained multiple submodels on each split training data and obtained prediction result with the submodels for each one remaining untrained split training data. Next, a model is trained on the data labeled ensemble of prediction result. Finally, in the inference phase, it outputs a prediction result by using mitigated model trained on the dataset labeled by ensemble prediction result. So based on KCD and SEDMA, our defense SEDMA also consists of 3 steps. First, SEDMA trained multiple submodels on each training data and aggregate the submodels in each combination. The aggregate models labeled the split training data not used for training in each combination. The labeled data is gathered as a dataset with soft label. Finally, in the inference phase, SEDMA output a prediction result by using a mitigated model trained on the dataset with soft labels. This is an intuitive explanation of SEDMA for 3 goals. For low attack accuracy, the model aggregation of SEDMA aims to reduce the overfitting of trained model by smoothing the information of trained data among multiple submodels. For high model accuracy, the model aggregation preserves the model accuracy, such as in federated learning. For low computational cost, SEDMA generates multiple aggregated models by averaging the models with combination of submodels. This is a setup of our experiments. We use 3 benchmark datasets, Purchase 100, Texas 100, and CIFAR 100. We use 4-layer MLP model for Purchase 100 and Texas 100, and ResNet 18 for CIFAR 100. We conduct 2 types of membership inference attack, single query attacks, label-only attack, in total 9 attacks. We compared with 5 defenses, ADREG, MEMGuard, KCD, SEDMA, and our defense, SEDMA. We set the hyperparameter of the defenses from each paper for good privacy utility trade-off like this setting. These are experimental results, 3 data sets and 2 types of attack. The vertical axis is model accuracy and horizontal axis is attack accuracy. The upper left shows the good trade-off between model accuracy and attack accuracy. Our defense SEDMA was superior privacy utility trade-off performance compared with other defenses. Also, this graph shows the processing time during training phase and inference phase. SEDMA has less training time overhead than SEDMA, but SEDMA, our defense is slightly more than KCD in training phase, but SEDMA has a superior privacy utility trade-off performance than KCD. In conclusion, we propose a new defense method using self-distillation with model aggregation against membership inference attack. Our defense mitigates the overfitting of training data by averaging multiple submodels trained on split training data. In addition, we achieved low computational costs because our defense aggregates the combination of submodels. We demonstrate that our defense outperformed previous defenses in achieving the lowest risk of membership privacy leakage in comparison with previous empirical defenses such as ADREG, MEMGuard, KCD, and SEDMA. In future work, we will applied our method to federated learning and large language models. That's all I would like to talk, so thank you very much.
Thank you very much for the talk. I was wondering if you could talk a bit more about how the inference phase works. So for a given data point, is it necessary to make sure that that in the combination model, you're not using one of the split data sets where that data point itself was during training, or if you could talk a bit more about that?
In the inference phase, we use just a mitigated model. So in training phase, we have to split data set and train multiple sub-models. But in the inference phase, we use just mitigated model only.
I guess what I meant is during the training phase, you split up into some number of data set partitions, and then when you're evaluating, for example, the membership inference accuracy, probably you used some of the points that were in the training data to see if the adversary. So I was wondering, when you're going to combine multiple models that were trained on several partitions. So do you ensure that mitigated model doesn't include a model trained on a data partition where the data came from? Not sure if the question is clear.
Yes, that's a good question. Actually, this is a try and error because our method is actually for a good trade-off. We use seven sub models. It's just hyperparameter, so it's a case by case for task or data set.
Okay, I'll just ask one question, which I think is borderline just an obligatory, uninteresting question for any sort of defense-style paper. I was wondering, because I don't think I spotted it in the presentation, what types of approaches you considered in terms of developing your own attack that was informed by how you created this defense, as opposed to, you have a number of comparisons to other defenses, but specifically, were you able to develop any better attacks versus the ones you were comparing your defense at being successful at resisting?
So you meant what types of attack is
given
evaluation?
given you designed a new defense, a more clever attacker knows what type of defense strategies you're taking. What approaches did you use to consider what clever attacks could be constructed against your new defense?
It's a tough question. So when I write this paper, we just 7 attacks, but Rabia said more attacks should be tried. So it's difficult to evaluate the differences.
All right. Let's thank the speaker. It looks good.